All right, so we're just going to look at another way to show conservation of energy, and we're going to use bar charts to do this. So the equation from previous is that initial total mechanical energy plus work equals final total mechanical energy. We can break kinetic energy down, but potential energy can be gravity or spring potential energy, and we've talked about that before and after. Okay, so all we're doing is extending potential energy into a couple of different aspects, either gravity or spring potential energy. So when we make work energy bar charts, one, initial and final states need to be analyzed so we can know the presence or absence of different forms of energy. We got to analyze the forces acting upon the object to determine if there's external forces and whether the work is positive or negative. And then we construct bars in the chart to illustrate the presence and absence of the various forms of energy. Okay? The exact height is not important. What is important is that the sum of the heights to the left is balanced by the sum of the heights of the right. And we'll show you some examples. So that's how you make bar charts. So here's our first example. We got a ball at the top, all right? It's not moving, so there's no kinetic energy. It's elevated, so there is potential energy due to gravity. But there's no spring potential energy because there's no springs and no work's being done to the ball. So initially, all we have is potential energy, gravity. And then at the end, it drops at the very bottom. The ball's moving, so there's kinetic energy. Potential energy, gravity, that's at the floor, so there's no height and there's no springs, so there's no potential. All there is kinetic. So total potential becomes total kinetic. We have to make sure that our bars, that total bar height's the same on both sides of the equal sign, which it is. All potential to kinetic with no work being done. All right, so here's another example. Skidding car. So the car's traveling, kinetic energy because it's moving. Potential energy, well, the height is 0, and there's no springs. But work is present, and it's negative because it's going back, right? There's friction, all right? So let's look at the end. So we have kinetic energy, and we have work. But how much work do we have? Well, at the end, the car's not moving, so there's no kinetic. It didn't gain height, so there's no potential, and there's no spring energy. So these are all negative, or 0. So there's nothing, which means added up at the left side should be 0. So all my kinetic has been transformed into friction or work energy, but it goes down. But these two added together then will be 0, just like it is over here. Okay, so here's our downhill skier. At the top, we have no kinetic. We have potential due to gravity because we're elevated, and we have no springs. Now, work is present because there's poles doing work, so we're going to use the poles to get ourselves down the hill. So we're going to add a little bit of work to this, all right? So we go 1, 2, 3, 4, 5, 6, 7. So we're at positive 7 on the left, which means we got to be positive 7 on the right. So now on the right, we get to B. Skier's moving, so there's kinetic energy. There's potential energy due to gravity because we have some height, but there's no springs, so therefore there's no potential energy due to springs. So I know what I have here has to equal what I have here. So this is 7. I have to have 7 blocks to the right. And to do that, I'm going to assume that my kinetic energy is greater than my potential, so I'll go 4 kinetic and 3 potential, but it adds up to 7. If you went 3 and 4, I don't think there'd be an issue. As long as it adds up to 7, I think you'd be okay. Now, what if there is no work? And we can look at bar charts this way too. So we got kinetic, potential, and total mechanical. With this type of bar chart, these two added together will equal total mechanical. So 0 plus 1, 2, 3, 4, 5 equals 1, 2, 3, 4, 5. 1 and a half plus 1, 2, 3 and a half equals 5. 1, 2, 3, 4, 5. I got 1, 2, 3, 4, a little less than 4, and I got a little more than 1. Add those together, we get 5. 5 kinetic, no potential, all 5 mechanical. But these two added together will equal mechanical. So let's look at the roller coaster. All potential, total mechanical energy does not change. As we get to B, right, we have some height and some speed, but added together equals that. At C, we have some less height, which means we have less potential, but we still have speed, but added together, it still equals total. At D, we're at the floor level, so there's no potential. It's all kinetic, which equals the total. And at E, we have a little bit of height and a lot of kinetic, but added together, it equals total. So let's do some examples. A ball is dropped from rest from a bridge. As the ball falls through the air, it encounters a small amount of air resistance. The final state of the ball is the instant before it strikes the water. Draw ball charts. All right. So the situation is a ball is dropped from rest from a bridge. The ball falls through the air. It encounters a small amount of air resistance. The final state of the ball is in the instant before it strikes the water. So initially, right, it's not moving, no kinetic energy. There's no spring. So there's a lot of energy that's considered potential due to gravity. So here's my, we'll move down a little bit. Potential due to gravity bar right here, okay? Then it says there's some air resistance. So air resistance is work, and it's going to be a negative work. So there's going to be a little bit of work here being negative. So we have positive and negative to start. At the end, it's at the bottom, so there's no potential energy. All it has is kinetic. So the kinetic energy is not going to be as high as the potential. In fact, it's going to be that much less. So we're going to say it's about this high. And my kinetic energy is going to be here. So total mechanical energy, not conserved, because we lose some to work in this instance. Bar charts make it a little bit easier than math. A spring gun is used to project a sponge dart into the air at an angle to the horizontal. The gun is held at a height of 1 meter before the trigger is pulled. The loaded spring gun is the initial state, and the sponge dart at its peak is the final state. Do it now. All right, so I'm going to read the next problem. A spring gun is used to project a sponge dart into the air at an angle to the horizontal. The gun is held at a height of 1 meter before the trigger is pulled. The spring gun is in the initial. The loaded spring gun is in the initial state, so the gun with the dart in it, and the sponge dart at its peak is the final state. So here's what we got. Right, we got here the dart launched. Will look like this. So the initial state's right here, and then the final state's going to be here. So let's draw the bar chart. So at the initial state, we have this thing that's it's a little bit above level, right? So it's going to have a little bit of potential energy due to height. So we'll give it that, right? And then it's also spring loaded. So we're going to talk about potential energy in the spring. So let's give it quite a bit here, all right? So that's what we got, right? We got gravity, we have potential energy from gravity, potential energy from the spring. We release it, all the spring energy then can go somewhere, right? Some of it goes to the height, so potential energy increases, but also the dart has some kinetic energy also. I would assume that as we get higher, potential energy will be greater than kinetic energy, so these two added together would be all the way to here, right? So we'll say about that much is potential. And then kinetic will be a little bit because it will have some speed. But this bar on top of this bar should equal this bar on top of that bar, or be pretty close. But our gravitational potential energy, right, increases. Our spring energy will decrease because it gets converted some to height and then some to the speed because the dart is moving. In a physics lab, a Hot Wheels car starts at an elevated position, goes down an incline to level ground, strikes a box, and skids to a stop. Consider 3 states for the car. State A at the top, state B before striking the box, and state C after it has been brought to a stop. Draw the diagrams, or draw the bar charts. Do it now. All right, so in the physics lab, Hot Wheels car starts at an elevated position, moves down an incline to level ground, strikes a box, and skids to a stop. So we want to consider state A. So we want to talk about from the top down to where it hits the box, and then after it hits the box and starts to skid. So I'm going to draw 2 different ones here. The first one's going to be at the top of the hill right before it hits the box. So at the top of the hill, I'm going to draw what that looks like. So it's going to look like this, right? Up here at the top of the hill, that's where we start. And then right here, before the car hits the big box, that's where we're going to finish, okay? So up here, we have purely potential energy. It's not moving yet, right? When it gets to the bottom, all that potential energy has then been converted to kinetic energy, and I think that'd be a pretty straight feeling that they both be the same height, okay? So potential gets converted to kinetic when we go from here to here. All right, that's pretty straightforward. Now, what about once the car gets stuck in the box, right? Once the car gets in the box, and then it gets to a stop. So here, right, here the car's inside the box, and that's C. So we're here, and if we look here, again, all we have going on is purely kinetic energy. So from B to C, we're on the floor and we're going fast, all kinetic energy. Now when it hits the box, it slows down because the box is pushing back, probably with friction and some applied force. But when it comes to a stop at the end, we have no kinetic energy, we don't gain height, and there's no spring. So the final energy is 0, which means all the work being done by the box is going to be the same length as this, just going in the opposite direction. And that work will be here. And kinetic energy then gets converted completely into work when it goes from fast to stopping because of friction. And that's how you draw the lines for that.